Yeah, good evening, everyone. Good evening. Good evening. Sir, we look at placements in IIT. If I clear gate, but have a year back, you have any past records? So I didn't know what exactly you are saying. Say properly. Say properly. You have backlog or what exactly? Bhushan, call everyone. Bhushan, call everyone so that we can start. Bhushan, call everyone so that we can start. Call everyone. Call everyone. Yeah. Good evening, Shikhar. Good evening, Bhushan. Yeah, let's start. So I'm going to cover 300 tough problems of discrete mathematics, GATE CSE for and GATE DA. For a few topics, GATE DA people may not have, but GATE CSE people, whatever I'm teaching, all will be there. For GATE DA people, few topics may not be there. Right? See the syllabus, plan accordingly. Right. So let's start now. If anyone having at any point of time any doubt, this is our WhatsApp number. You can ping. We will add all of right. If you have any doubt, you can ping us. So we will add you in the group. WhatsApp group is there. There you can ask all your doubts happily. So let's start now. So, okay, fine. So 1, 2, 3. Ready, steady, go. 1, 2, 3. Ready, steady, go. Can we go ahead? Can we go ahead? Can we go ahead? Hello? Hello, can we go ahead? 1, 2, 3, ready, steady, go. Yeah, everyone can try, everyone try. Go, right? Everyone say, ready, steady, go. Everyone can type, ready, steady, go. Everyone can type, ready, steady, go. Go ahead, go ahead. Hello? Everyone can type, ready, steady, go. Everyone. Arey, Boshan, say yaar. Boshan, say yaar. Shikhar, say man. Kef, say. Ready, steady, go. Ready, steady, go. Arey, Kef, say properly yaar. Kef, say properly yaar. Ready, steady, go. Ready, steady, go. Chalo. First problem. Yeah, can you go ahead? What is the answer for this? What is the answer for this? If G is a forest with n vertices and k connected components, how many edges does G have? If G is a forest with n vertices and k connected components, how many edges does G have? Go ahead. Go ahead, everyone. Everyone, go ahead. Everyone, go ahead. G is a forest with n vertices and k connected components. How many edges does G have? So remember. So if you observe clearly, see this one. If you observe clearly, Prim's algorithm don't create forest, but Kruskal algorithm may create forest. Kruskal algorithm create forest. Remember, forest means. Remember, Prim's algorithm, Kruskal algorithm, both are for spanning tree purpose. Spanning tree means no cycle. Kruskal algorithm, Prim's algorithm for spanning tree purpose. Spanning tree means no cycle. No cycle. But Kruskal algorithm will connect to, right? Kruskal algorithm may create the disconnected graph. What does it mean? Disconnected trees. Remember, forest is nothing but collection of trees. Forest is nothing but a collection of trees. Remember, this is a forest. This is a forest. When you say forest, collection of trees, remember, this is a one tree. This is one more tree. This is one more tree. And so on, and so on. This is one more tree. So it is almost like first component. It is the second component, which is nothing but a tree. It is the third component. It is the k minus 1 component. It is the kth component. Collection of trees. Remember, everything is a tree. Remember, from today onwards, if anyone say to you, G is a forest with n vertices and k connected components, what is the answer? Remember, forest is nothing but collection of trees. Collection of trees, where every tree is a one component. So try to understand. It is a forest. It is a forest. Please be careful. Now, one more small question I want to ask you. Can you help? Every tree should contain minimum one node or not? Every tree should contain minimum one node or not? Of course. Every tree should contain minimum one node. When you say three components are there, right? Every component should contain minimum one node. So remember, so when you say k components, one vertex already there here, minimum one vertex already there here, minimum one vertex. Try to understand. So there are k components are there, means every component contain at least one vertex. Now try to understand. So total vertices are n, right? Total vertices are n. If you do n minus k, right? So left out vertices are n minus k. Total vertices are n, right? After deleting, because every component contain at least one vertex, right? Left out vertices are n minus k. Left out vertices are n minus k. If anyone having small doubt also, let us assume that number of vertices are 20. Assume number of components are assume that number of components are 8. Right? Vertices are 20, components are 8. So 20 minus 8, which is going to be 12. So remember, 12 vertices are left out. 12 vertices left out. Every component I kept one vertex. So 12 vertices are left out. From now onwards, understand. 12 vertices are left out. From now onwards, understand. Let us assume that I have 12 vertices left out. 20 minus 8 is going to be 12 vertices are left out. Now see what I am doing. A, B, C, D, E. I already kept. Now 12 vertices are left out. Now let us assume that 13th, right? 12 vertices are there. Out of those 12 vertices, one of the vertices is assume F. So I kept F. Remember, I kept F in the first group. Remember, because of it is a tree, forest is nothing but a collection of tree. Remember, every vertex will bring one edge. So because of F, one edge came. right? Next one, F is over, E, F, G. I kept one more vertex G. Suppose if I keep one more vertex G, every vertex will bring one edge only. So G will bring one more edge. And next one, some people are asking, G, what about H, sir? You can keep H wherever you want. You can keep in the first component also, second. Remember, every vertex will bring one new edge. H also will bring one new edge. Next one, if you keep I, it will also bring one edge. Every vertex, left out vertices, every vertex will bring one edge. So what I mean to say is 12 vertices are left out, it can bring 12 edges. Every vertex will bring one edge, so 12 edges. So n vertices are there, k components are there, number of edges possible is n minus k, n minus k edges possible. Yeah, is it fine now? Is it fine now? Left out vertices are n minus k. For every vertex, one edge you will get. If you add f, whichever group you want, you can add. F purpose, f if you add in one of the component, one edge will come. If you add the G in some other component, one more edge will come. Every vertex will bring one edge. Every vertex will bring one edge. Like that, 12 times, 12 edges will come. Like the 12 times, 12 edges will come. Like the 12, right, like the 12 times 12 edges will come. So if anyone having small doubt also, if anyone having small doubt also, if anyone having small doubt also, you can check one small example. Many people done with by taking numerical, that is also correct. Those people who are done with numerical, those people who are done with numerical, that is also okay. By taking numerical, people done, that is also perfect. You can, if you want, you can check. There are 4 components. Remember, forest is collection of trees. Forest is a collection of trees, remember. So now if you observe clearly, vertices how many? 3 plus 4, 7. 7 plus 1, 8. 8 plus 2, 10. Vertices are 10. Edges are going to be, edges count also. 2 plus 3, 5. 5 plus 1, 6. So 10 minus 6. 10, right? So edges are 6. Components k is going to be 4. So 10 minus 4, which is going to be 6. Same thing. Some people done with numerical example, that is also okay. Those people who done with numerical example, that is also okay. Do whatever way you want, but do meaningfully. This is the almost proof for this. It will be useful for further problems also. Please, can you take care? This is useful for further problems also. Today onwards, remember, forest is nothing but collection of trees. Forest is nothing but a collection of trees. Try to understand this. Forest is nothing but a collection of trees. Some people are thinking disconnected graph is a forest. No. When you say disconnected graph, every subgraph may contain cycle. But when you say forest, it is a collection of trees. Right? Let me write now. Disconnected graph. Disconnected graph is different. Forest is different. Disconnected graph is collection of graphs, not trees. Collection of graphs. Disconnected graph is nothing but a collection of graphs. Forest is nothing but a collection of trees. Collection of trees. I hope everyone is fine. So you can do manual checking also. If you get this proof also, excellent. If you get this proof also, excellent. Let's move to next problem. If everyone okay, are you comfortable with this or not? Let's check. Are you comfortable with this or not? Let's check. Are you comfortable with this? Answer is C. Don't by heart. Answer is C. Don't by heart. Some people what they are doing is they are substituting in the formula. Some people what they are doing is they are substituting in the formula. Sometimes he will give in examination. Sometimes he will give like this one. In the forest, 50 vertices are there. In the forest, 50 vertices are there. And one more, 28 components are there. Right? Number of edges how many? He may not ask. He may not give formula. He may not give formula. Then you will stuck. In a forest, 50 OTCs are there, 28 components are there, how many edges are there? Then you will stuck. If formula is not given, you want to ask numerical type question, then you will stuck. So if possible, know the meaning. If possible, know the meaning. If possible, know the meaning. Don't by heart everything. Yeah, worst case you will do manual checking. I'm absolutely fine. Right? In the examination, don't try for proofs. Examination, don't try for proofs. Before exam, take care. How it came. Before exam, take care how it came. It will be useful further. Yeah, go to the next problem. Go to the next problem. Try this. What is the answer of this? What is the chromatic number of n, right? What is the chromatic number of n? N would take simple connected graph which does not contain any odd length cycle. What is the chromatic number of a n would take simple connected graph which does not contain any odd length cycle? Someone is saying 23 edges and subtract properly subtract. Right? 50 minus 28, 50 minus 28, 22. Answer is 22. That is okay. Now go to next problem. Now go to next problem. Yeah, can you try what the answer? Can you try what the answer for this? Go ahead, everyone. Everyone try. What is the chromatic number of n vertex simple connected graph which does not contain any odd length cycle? Everyone try. Yeah, what is the answer? Please let me know what is the answer. What is the chromatic number of n vertex simple connected graph? Remember, by mentioning the connected, by mentioning the keyword connected graph, minimum 2 colors. Chromatic number means minimum number of colors you have to give to vertices so that no adjacent two people contain same color. That is called chromatic number. Minimum colors you have to give. So let's see this one. So if at all connected graph, minimum 2 colors. Minimum 2 colors. Connected graph. Whenever people say connected graph, minimum 2 colors. But he said that no odd length cycle. Remember, in the given graph, odd length cycle not there means it is a bipartite graph. Odd length cycle not there. In the given graph, odd length cycle not there. It is a bipartite graph. So if you want, you can verify. If you want, you can verify. So 1, 2, 3, 4, 5, 6, 7. See this one? Going here, right? Going here. See this one? Coming here. So it is a even, right? So going here, coming here, but it is not a cycle. Again going here, again coming here. See this one? I think again, right? No cycle. Again, no cycle, right? So until now, everything is fine now. Until now, everything is fine. Now see this one. Going here, coming here. So it is odd length. It is an even length cycle. It is an even length cycle. So because of even length cycle, within the M, no edge. Within the N, no edge. If at all odd length cycle is possible, within M, edge will come. Or within N, edge will come. So remember, in the given graph, odd length cycle is not there. It's a bipartite graph. Bipartite means maximum one color, maximum two color. Every bipartite graph required maximum two colors. Max two colors. When you say bipartite, maximum two colors. When you say connected graph, minimum two colors. Minimum two, it is saying maximum two. So overall, if you observe, two only. Two. Answer is two. So from this problem, try to understand a simple connected graph which don't have odd length cycle. Odd length cycle not there means bipartite graph. Not contain odd length cycle. So bipartite. Yeah, so yeah, maybe you can post in the group gate questions you can post in the group. If I feel some problems are good, I will definitely cover. Right, in the given graph no odd length cycle means it is a bipartite graph. In the given graph no odd length cycle, so it is a bipartite graph. Bipartite graph means I think for n people one color you can give, n people you can give one color. Two colors are more than enough. Every connected graph, minimum 2 colors required. Every bipartite graph, maximum 2 colors required. Yeah, you can post tomorrow, right? I am going to explain. You can post. I already asked in the group many times. If you find out some difficult question, please post so that I can explain. Yeah, fine. Is it okay now? Answer for this one is B. Answer for this one is B. Is it okay? What is the chromatic number of an n, right? What is the chromatic number of an n vertex simple connected graph which does not contain any odd length cycle? Which does not contain any odd length cycle. What is the chromatic number of an n vertex simple connected graph which does not contain any odd length cycle? Answer is 2. If anyone having any doubt, let me know. Odd length cycle means it is not bipartite. Can we move to next? Respond, yaar. Those people who are watching, array man, respond. Coming and sitting, coming, sitting, coming, sitting. No response at all. Coming, sitting. Array, respond, yaar. Answer 2, na? How 3? Array, Abhiraz, answer 2, na? How 3? Go to next question. Yes, exactly. Exactly. Let's go to next. Can you try this? Which of the following is true for any simple connected undirected graph with more than 2 vertices? Which one of the following is true for any simple connected undirected graph with more than 2 vertices? With more than 2 vertices. Which one of the following is true for any simple connected undirected graph with more than 2 vertices? Get exam questions, all questions are like this. Little tricky. Small doubts will be there. Little tricky. Which one of the following is true for any simple connected undirected graph with more than 2 vertices? Everyone try. So I think these kind of things by taking example you can try. Right? Connected graph with more than 2 vertices. More than 2 vertices I took. Option 1 saying that no 2 vertices have same degree. See, all are having 0 degree. No 2 vertices having same degree. So it's wrong. Next one, at least 2 vertices with the same degree. At least 2 are they. If I keep like this one, right? At least 2 people. If I keep like this one, at least 2 people. If I keep like this one, at least 2 people. If I keep like this one, right? At least 2 people. I think it looks like correct. Next one, at least 3 vertices have same degree. At least 3 vertices need not be, right? So if you observe clearly in this problem itself, it is failing. All vertices having same degree, no. So answer is second option, everyone know. Answer is second option, everyone know. It may come for 1 mark. It may come for 1 mark. Can you try this? Which one, right? What is the chromatic number for the following graph? Can you find out chromatic number? For these two graphs, find out chromatic number. For these two graphs, find the chromatic number. For these two graphs, find the chromatic number. For these two graphs, find the chromatic number. Yeah, let's try. Let's try chromatic number for every person. Let's try chromatic number for every person. So I'm trying this. So remember, at anywhere, triangle there like this. At anywhere, triangle like this. So three colors, three chromatic number. Triangle is there. So three chromatic number. Everyone know. Next one. See everyone, three chromatic number. Suppose assume that in the graph, maximum degree, in the graph, maximum degree, in the graph, maximum degree is 5. In the graph, one vertex having maximum degree 5. Then chromatic number, right? Maximum, then chromatic number, maximum chromatic number possible 6. If maximum degree is 5, right? Maximum chromatic number, right? Chromatic number at max 6. Chromatic number at max. Chromatic number at max 6. So something like complete graph. Something like complete graph. If you observe a complete graph, K6 assume every 1 degree 5. Assume that a complete graph with 6 vertices, K6, every 1 degree 5. So maximum degree 5. If you see the chromatic number 6, because every one is adjacent. So if the maximum degree is 5, chromatic number is at max 6. Right? This also, if anyone don't know, please remember. At maximum. Maximum degree is 5, chromatic number at max 6. Next one, triangle is there, chromatic number 3. Not minimum, not maximum, 3. Next one. If it is a planar graph, if the given graph is a planar graph, chromatic number at max 4. At max 4. So try to remember all these things. Triangle, chromatic number 3. Maximum degree 5, chromatic number maximum 6. Planar graph, chromatic number is at maximum 4. Every planar graph is 4 colorable. Means it don't take more than 4 colors. Someone is saying 3 both. Second one is 3. So let's try this. Yeah, I think someone is saying that both 3. I will try this. Let's start one by one. It is the C1. It is the C2. Right? It is the C3. It is the C2. Triangle will take 3. Right. Next one. Next one. It may be C2. It is maybe C1. Check if I keep any color, what is the problem? C1, C3, C2 I cannot keep. So I can keep here. I can keep here. I can keep here C2. I can keep here C1. I can keep here C1. Check. Is it fine now? First diagram is 3. Is it fine now? Is it fine now? First diagram is 3. However, remember, chromatic number finding is undecidable problem. There is no algorithm. Manual checking you have to do. There is no algorithm. Manual checking you have to do. That is the reason they given small graph. Big graph is given. Finding the chromatic number is undecidable problem. There is no algorithm to find out chromatic number. There is no algorithm. So we have to do hit and trial only. Brute force method only we have to use. So I got answer as 3. And one more thing. First question I want to ask you. Is it planar graph? Can you check? Is first graph is planar graph? See, no edge crossing. No edge crossing. So first graph is planar graph. Because the first graph is planar graph, it don't take more than 4 colors. Because the first graph is a planar graph, it don't take more than 4 colors. Number of colors should be either 4 or less than 4. Now, because if it's a planar graph, number of colors should be either 4 or less than 4. That is the one thing. Next one. What is the maximum degree available in the given graph? I think C3, if you see the graph vertex G, which contains 6, if the maximum degree is 6, right, at max it will take 7 chromatic number. At maximum, it will take 7. It don't take more than 7. But because of it's a planar graph, it don't take 7 also. It will take maximum 4. So answer should be either 7 or less than 7. In the next step, answer should be either 4 or less than 4. So we got answer 3. That is fine. We got answer 3. That is the reason these all theorems will give some boundary. Right? Planar graph is a 4 colorable. Planar graph is a 4 colorable. Right? It don't give exact answer. It will give upper bound. 4 colorable means maximum it will take 4 colors. They don't give, see, because of it is undecidable, there is no one who is going to give answer to you. Except your brain, no one is going to give answer. These all theorems will give boundaries. At least they will give some boundary. Oh, maximum degree 6. Oh, chromatic number 7 or less than 7. Next one. Oh, it's a planar graph 4 or less than 4. I tried. I got to know 3 itself is enough. Please verify. Please make sure there is no algorithm. You have to do manually. If anyone got 4, right, please recheck properly. Okay, let's go to second diagram. So first one is chromatic number. Chromatic number. Assume that Cn means chromatic number. Assume. So it is 3. Let's go to second diagram. So let me try. Here. C1 here. C2 here. C3 here. C3 here. Now I think C1, this one is adjacent. So I cannot keep C2. I think I can keep C3. C1 and right. So A and D is adjacent. A and D is adjacent. So A is C1. D I kept C3 so that C2 is adjacent. Next one. I think I can keep here. C1. I can keep here C2. Check if I done anything wrong. Check if I done anything wrong. So, and one more thing. So second diagram also planar graph because nowhere edge crossing. Nowhere edge crossing. Second diagram also planar. So maximum number of colors are 4 or less than 4. Maximum number of colors needed is 4 or less than 4. Maximum 4 or less than 4. So by luckily we got only 3. So I think second graph chromatic number is 3. Second graph chromatic number is 3. I hope everyone is comfortable. I hope everyone is if at all you are okay, please comment in the comment section so that I can proceed to the next problem. Comment in the comment section. Remember, all theorems will give boundaries. All these theorems will give some boundaries. Triangle. So exactly 3 colors required. Next one, right? Planar graph, maximum 4 colors required. Maximum degree 5. So chromatic number maximum, right? 6 required. Yeah, if everything is okay, those people who are okay, please type, go to next problem. Please type everyone, go to next problem. Please type everyone, go to next problem. Someone is saying, sir, is finding planarity of a graph is decidable. Yes, because if the graph don't have K5 or K33 is a planar. In the given graph, if you don't find out K5 or K33 is a planar graph. It is having some rule at least. K3 or K33 or K5. Now let's go to next one. Chromatic number is undecidable. Yeah, let's move to next problem. Yeah, can you try this? And those people who are watching, please like the button. First, please like the button. And if anyone is not subscribed, please subscribe. If anyone is not subscribed, please subscribe. And if anyone is not liked, please like. If anyone not liked, please like. Everyone, try one time. Yeah, can you try this? This is the interesting problem. Can you try? This is the interesting problem. Can you try? In n-vertex simple graph, what are the maximum edges you will keep? Such that graph is disconnected. What are the maximum number of edges you will keep in the graph such that graph become disconnected? Everyone try. In the given simple undirected graph with n vertices, what are the maximum number of edges you will keep inside the graph such that graph become disconnected? Exactly. Abhiraz, thank you so much. Exactly. So you want maximum edges. Listen, you want maximum edges. When you say maximum, there is a concept of complete graph. When you say maximum, there is a concept of complete graph. See, with n vertices, so if you want maximum edges, you can keep kn. With n vertices, if you want maximum edges, so maximum edges with n vertices, kn. Complete graph with n vertices. But he's saying that graph should be disconnected, but kn is a connected. So what you can do is, right, you can make disconnected kn minus 1 one side, one vertex another side. then the graph become, let us assume that, n value 6 assume, n value 6 assume. Then in the first diagram, if n value 6 in the first diagram, right? So these many will come. N value 6. In the first diagram, these many will come. All people are adjacent. So how many edges are there? In the first diagram, how many edges are there? You know very well. 6 vertices, every vertex degree is 5 by 2. N into n minus 1 by 2. I think 6 5 30 by 2, 15. 15 edges are there, count. But the question here is, you want to make the graph as disconnected and maximum edges. When you say maximum, complete graph required. When you say maximum, complete graph required. Can you see this one? So 5 vertices you take. 5 vertices you take. One vertex outside. So here, so if you observe clearly here, it is became K5. It is a K6. So here 5 into every 1 degree 4 by 2. 20 by 2, 10. 10 edges. Some people are asking, sir, can I take one more edge? If you take one more edge, definitely not connected. If you take one more edge, not connected. Add one more edge, not connected. Add one more edge, not connected. So now listen everyone. If at all n value 6 this is. So only n is there, n into n minus 1 by 2. If at all here n is there, so I think it became n minus 1, it became n minus 2. N minus 1 into n minus 2 by 2. If at all n value 6, so here n into n minus 1 by 2. Here n value 6, so right? Here 5 only, 5 vertices only, here 1 vertex. So 5 into 4 by 2, n minus 1 into n minus 2. Remember, this is nothing but n C2. This is nothing but n minus 1 C2. N minus 1 C2 is nothing but n minus 1 into n minus 2 by 2. Right? N C2 is nothing but n into n minus 1 by 2. So answer is the D option. Thank you so much. Thank you so much. The people who said answer is option D. Thank you so much, Bhushan. Thank you so much, Abhiraz. N minus 1 complete graph. So remember, in the disconnected graph, if you want maximum edges, this is the way you have to follow. In the disconnected graph, if you want maximum edges, this is the way you have to follow. Right? In a simple undirected graph with n vertices, what are the maximum number of edges that can have keeping the graph disconnected? So remember everyone, if you want a graph with maximum edges but disconnected, you have to go like this. Can we go next? Can we go next? Can we go next? Hello? Hello? Can we go next? Let me know if anyone having small doubt also, small issue also. This is the very, very good problem. This is the very good problem. This is the very good problem. Suppose he may ask the same question like this. He may ask you same question like this. He may ask the same question like this. What is that one? N vertex simple graph. N vertex simple graph. You want to make the graph as disconnected. You want to make the graph as disconnected. You want maximum number of edges. But remember, every subgraph should contain minimum 2 vertices. So what is the answer? Same problem. But when you say disconnected, there are some subgraphs are there. Right? Every component should contain minimum 2 vertices. With n vertices, what is the maximum number of edges possible? where graph is disconnected and every component contain minimum two vertices. What is the answer? Means you cannot keep outside one vertex. You have to keep outside two vertices. But I want maximum edges. In a n vertex simple graph, maximum number of edges possible how many? Where graph should be connected, where graph should be disconnected, and every component should have minimum two vertices. Can anyone say what is the answer? Okay, two people you have to keep outside. Two people you have to keep outside. Means out of kn, two people remove. Two people remove. Out of kn, two people if you remove, kn minus 2. Kn minus 2, how many edges possible you do? Because of outside two people are there, one edge will come. Outside two people are there, so one edge will come. It will become. So what is the answer? N minus 2 into n minus 3 by 2 plus 1. This is the answer. So which is also, if you want, you can write n minus 2 C2 plus 1. You can ask whatever way you want. He can ask whatever way you want. He can ask the same question like this one. How many, right? See, how many maximum number of edges possible in a simple graph? How many maximum number of edges possible in a simple graph where graph is disconnected? Where graph is disconnected. So he may ask you where every subgraph contain, or every component contain minimum four vertices. Minimum four vertices. Like that he will ask. Like that he will ask. So accordingly you can plan. I think everyone is absolutely fine in this problem. Everyone is fine, absolutely fine in this problem. Let's move to next problem. Let's move to next one. Let's move to next one. Yeah, can you try this? Can you try this? It is also interesting problem. Can you try this? It is also interesting problem. Can you try this? Everyone try. It's a problem number 6. It's a problem number 6. Let's see how many people will give. Which statements are true? A simple graph is necessarily connected if number of edges are n minus 1 into n minus 2 by 2. Is first statement is true or not? You know this is going to be, listen, you know this is going to be number of edges possible in the k n minus 1. This is going to be number of edges possible in the k n minus 1. Now see the answer. Now see the answer. Now see the answer. N, right? N minus 1 into n minus 2 by 2 edges. Suppose assume that n value 6. Suppose assume n value 6. So n value 6. Now I am taking n value 5 here. 5 people I am taking. So it is a K5. It is a K5. See everyone, it is a K5. Right? It is a K5. Understand, it is a K5. Here one vertex. Now listen, Already in the K5, n minus 1 into n minus 2 by 2. Edges already there. Here already n minus 1 into n minus 2, right? Edges are already there because here n minus 1 vertices are there. With n minus 1 vertices, the number of edges possible is this one. Now listen, from now onwards, listen, from now onwards, see, number of edges are more than this. Means, right, for this one more edge maybe you added. Remember, comparing this one E bigger, comparing this one E bigger. What is the meaning? Suppose n value 6, so right, if it is a right n value 6, so if it is belongs to inside 5 into right 5 into 4, 20 by 2, 10. So this is 10. Suppose assume that it is 11. That means one edge is there like that. Guarantee that it is a guarantee that it is connected. A simple graph is necessarily connected if number of edges are more than n minus 1 into n minus 2 by 2. Is it true or false? Please check. S1 is a true statement. Am I right or wrong? The maximum number of edges possible in a simple graph which is disconnected is n minus 1 into n minus 2 by 2. But more than that edges are there means compulsory connected. In a simple graph, maximum edges possible, right, by disconnecting. In a simple graph, maximum edges possible by disconnecting n minus 1 into n minus 2 by 2. But you have more than that edges. Compulsory graph is connected. Compulsory graph is connected. Suppose assume that n into n minus 1 into n minus 2 by 2. If this is bigger, then graph is not connected. I cannot give guarantee. But when you say left bigger, E bigger, guarantee graph connected. No doubt at all S1 is true. No doubt S1 is true. What about S2? Can anyone help me? What about S2? Everyone try. What about S2? Everyone try. What about S2? Check properly. What about S2? A simple graph with n vertices and k components has at least n minus k edges. Now I want one small question. In this problem, at anywhere he mentioned, in the S2 statement, at anywhere he mentioned forest. In the S2 statement, at anywhere is he mentioned forest. S2 statement at anywhere is he mentioned forest. No keyword is there forest. But he said that, listen, he said that k components are there. Remember, every component may be tree, may not be tree. K components are there. Every component may be tree, may not be tree. Because nowhere he mentioned forest. Forest is nothing but a collection of trees. But when you say graph, collection of some subgraphs. K components are there. Collection of K subgraphs. Collection of K subgraphs. Right? Collection of K small graphs is a simple graph here. No forest, nothing. Now observe. Everyone observe. Everyone observe here. N value assume, this one. N value assume 20. K value assume 8. N value assume 20, K value assume 8. Now understand. Now understand this. See everyone, now understand this. It is a component C1, component C2, component C3, and so on, and so on. Component C7, component C8. Because you have 8 components. You have 8 components. But remember everyone, every component should contain at least one node, A. Every component required at least one node. Every component required at least one node. Okay. Every component required at least one node. That's okay. Now see the answer. N value 20, K value 8, 20 minus 8. Totally 12. Right? Totally 12. Remember, 12 vertices are not went anywhere. 12 vertices are out. See this one. Everywhere I kept one vertex because every component required minimum one vertex I kept. So remaining, right, left out, 12 vertices are left out. 12 vertices are left out. Now observe. Now observe everyone. Very interesting line. Now observe everyone. Now observe everyone. 12 vertices are left out. Those 12 vertices, this one, 12 vertices are left out. Those 12 vertices are, assume F is the first vertex, G is the next vertex, H is the next vertex, I is the next vertex, J is the next vertex. Like that, assume 12 vertices are there. Some people are asking, sir, where I will keep these? You keep wherever you want. In any component you can keep. In one component also you can keep. You can keep in the many components also. It's up to you. Let us assume I kept F here. Listen, whenever I will keep F here, one edge will come. One edge came. Some people are asking, sir, where I will keep G, sir? You can keep G in any component. You can keep G in the C1 component only. Let us assume that I kept G in the C1 component only. Then this is also one edge, this is also one edge. You can keep more edges also. Some people are saying that in the component how cycle is allowed. There is nowhere he mentioned forest. K components are there. A simple graph contains K components. Every component is a connected graph. Every component is a connected graph. It may contain cycle, may not contain cycle. So remember G, right? G generated two edges, right? G generated two edges. Next one, G, I added H also, assume. I added H also. One edge here, two edge here, three edge here. Maybe three edges will come. So what I mean to say is, if at all it is a forest, for every vertex, one edge will come. Because of it is not a forest, for one vertex, maybe more edges will come. So remember, 20 minus 8, which is going to be 12, which is going to be 12. Remember, 12 edges minimum. Minimum 12 edges will come. Remember, minimum 12 edges will come. Minimum 12 edges will be there. It is not every time one, sometimes increase also. Minimum 12 edges are there, which is nothing but minimum n minus k edges. At least n minus k edges. At least n minus k edges, right? Remember, it's a very nice statement. A simple graph with n vertices and k components has at least n minus k edges. A simple graph with n vertices and k components, right, has at least n minus k edges. At least, because 12 minus 8 if I do, right, so 20 minus 8 if I do 12 there, 12 vertices are left out. Every left out vertex, if you add, you will get minimum one edge. Sometimes two edges will come, sometimes three edges will come. At least n minus k edges. It is a true statement. At least 12 edges are 20 minus 8 is 12. At least 12 edges are there. It is like a previous problem only, but forest is not mentioned. Be careful. Forest is not mentioned. Be careful. Forest is not mentioned. Be careful. So if you okay with this, if anyone having any doubt in the sixth problem, let me know. If anyone having any doubt in the sixth problem, let me know. Hello? If anyone having any doubt in the sixth problem, let me know. These are very, very dangerous statements. These are very, very dangerous statements. These are very, very sensitive statements. Very, very sensitive statements. Everyone, see, all are same, yeah. Algo is same. Algo same. Discrete mathematics same. Everything same, yeah. TOC same. In my opinion, algorithm same, discrete mathematics same, TOC same. In my opinion, these three subjects are same. All are logics. Small logics. Algo, discrete mathematics, TOC similar. If forest is there, not at least n minus k edges. If forest is there, N minus k edges, exactly n minus k edges. Forest there, exactly n minus k edges, because every time one edge only will come. Forest is not there, at least n minus k edges. At least is the keyword. See, same thing. If you observe clearly, this one, listen, this one, few minutes back we done one problem also. Let's go there. See everyone, this problem. Can you see this? Can you see this one? Can you see this one? If G is a forest with n vertices and k component, then how many edges does G have? See, minimum not there. How many edges G have? How many edges G have? N minus k. It is not at least two. Exactly. It is exactly. It is exactly. It is exactly because of forest. Because of forest, no cycle possible. Because of forest, no cycle possible. Then more edges cannot come. It is exactly right. Because the forest is not there here. At least n minus k edges. At least n minus k edges. Anyone? Are cave you got or not? Are this cave is playing cricket, yaar. He left discrete mathematics. This cave is playing the cricket. He left discrete mathematics. He's playing cricket. Arey, Kf, you got or not? He left discrete mathematics. He's playing cricket. These are very tricky things, small tricks. Small tricks. To me it looks so easy because many times I done. See, many times I prepare tests also. Many times I prepare tests also. Right? I taught so many batches. Many times I prepare test also. That is the reason these are looking to be so simple. But when you are listening first time, guarantee some problems are there. Guarantee you may find out small difficulty. Small difficulty you may find out, because of I done many times. To me it looks it's okay. To me it looks so it's okay. See, very simple. Because of it is not a forest. To see this one. Because of it is not a forest. To see this one. Everywhere keep one person first. Because when you say k component, every component required one vertex. See, everywhere I kept one vertex first. So the left out vertices, if you see, 12 vertices are left out. See, the left out vertices are 12 vertices. 12 vertices are left out. 20 minus 8, 12. But those vertices, assume that F, G, H like that. So F I kept in the first component. So how many edges came? One edge came. Next one. So G also I kept in the same. How many edges came? There may be chance that two edges also can come. Two edges also can come. So when I keep G, this is one edge. This is one edge. Two also can come. When I keep the H also here, so three edges came. One here, two here, three here, three edges. Means what I mean to say is, with the left out people, every person not only giving one edge, more edges also he can give. Every person can give more edges also. What one thing guarantee, minimum one edge will come. Every person will give minimum one edge. Minimum one edge. More also he can give. More edges also he can give. That is the reason. Answer is at least n minus k edges. At least n minus k edges. That is the minimum. 20 minus 8, 12. Minimum 12 edges will be there. Minimum 12 edges, because cycle also allowed. See, here cycle allowed. Cycle allowed, so more edges will come. Cycle allowed, so more edges will come. Srishti, are you there? Srishti, are you there? She's gone. Srishti gone for dinner. Srishti went for dinner. Arey, this dog Ashwini came or not? This dog Ashwini came or not? Every day he will say discrete mathematics, discrete mathematics, discrete mathematics. There is a one dog is there, his name is Ashwini. That dog will bark every time. Every time that dog will bark. DMS, 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 DMS. Whenever DMS going on, he is sleeping. Whenever DMS going on, that dog is sleeping. Whenever DMS not happened, that dog is barking. In Delhi at Jantar Mantar, that dog is barking DMS, DMS, DMS. In Delhi, one famous area is there, Jantar Mantar, right? Whenever you want to do some unnecessary thing, go to Jantar Mantar and do there. I seen Ashwini Sharma many time. Ashwini Sharma many time at Jantar Mantar. At Jantar Mantar is doing DMS RIC. DMS RIC Reddy sir. DMS RIC Reddy sir is keep on doing dharna. But when I started, that dog is not there. When I started, that dog not there. Famous for protesting. Yes, exactly. Exactly. So that dog may be there at Jantar Mantar. Please go and meet. Please go and meet that dog at Jantar Mantar. That dog may be available. Please go there. Right. Let's move to next problem. So answer for this problem. Both the statements are true. Both the statements are true. Sir, Reddy sir, these are looking so danger. Bhaiya. Some people are saying, Reddy sir, these are looking danger. Can you see this? Then what is the meaning of tough problem? What is the meaning of tough problem here? Reddy sir, these are looking very danger. Then what is the meaning of tough? What is the meaning of tough here? Chalo. Next. Go to the next problem. Go to the next problem. Can you say what is the answer of this? Yeah, try everyone. Problem number 7. Everyone try. Let's see how many people will go. Yeah, let's see one small line. See this one. If S and T are two different trees, see this one. Trees. So if S and T are two different trees, see, two different trees. If S and T are two different trees, now observe. Sum of degrees. But remember, S also contain V vortices, E edges. T also contain V vortices and E edges, but different. There are some differences are there, right? S and T are two trees, right? S and T are two trees where V vortices are there, E edges are there. That's okay. Now observe sum of degrees in S. Sum of degrees. Let us assume that sum of degrees is 18. Assume this is sum of degrees in T also. Let us assume this is also 18. So 18 can be written as 2 into 9. 18 can be written as 2 into 9. Remember, sum of degrees is 2 into E, number of edges. So number of edges are 9. So edges are same. When you say these two are same, right, definitely this can be written as 2 into E. So number of edges also same. And one more thing I want to ask you, if number of edges are 9, number of vertices are 10. If number of edges are 9, number of vertices are 10, then vertices also same. Then vertices also same. Edges same, vertices same, exactly same. Vertices same, edges are same, exactly same. Is it okay? Sum of degrees are 2 into E. 2 into E, 18 is U. Sum of degrees in T also 18. 2 into E. Fine. Both are 2 into E. 2 into 9, 2 into 9. Right? So 9 edges. When you say in that tree, listen, in that tree, two vertices are there, one edge. In that tree, right, there are three vertices, two edges. So one less. Vertices are 3 means edges are 2. So I think vertices and edges both are equal. So exactly they both are same. Cardinality of S is equal to cardinality of T. Means number of vertices are equal, number of edges also equal. Answer is, if anyone having any objection, let me know. If anyone having any objection, let me know. Any objection, let me know. If anyone have. If anyone having any objection, let me know. Both. He could have mentioned. Right? But anyhow, both are same. You could have mentioned both. Number of edges in both of them same, right? But see, when you say cardinality, number of people, cardinality of vertices, cardinality of edges, you could have mentioned. But anyhow, both are same, right? So there is no objection. Can we go further? When you say that right, when you say that right, mod operator, when you say that mod operator, so cardinality of S is equal to cardinality of T. So vertex cardinality, edge cardinality. So both are equal. Vertex cardinality, edge cardinality, both are equal. So there is no problem. So cardinality of edges same. Cardinality of vertices also same. So they both became same. Right? Because of they both are same, that is the reason he didn't mention. Suppose assume that they right something is different, he will mention in the problem. What is the vertex cardinality? What is the edge cardinality? You could have mentioned. You go to this problem. This is also interesting. Can you go there? Can you go there? Start. Start answer for this. Yeah, what is the answer for this? Everyone, let G be a complete undirected graph on 6 vertices. If vertices of G are labeled, then the number of distinct cycle of length 4 in G equal to. Let G be a complete undirected graph on 6 vertices. If the vertices of G are labeled, then the number of distinct cycle of length 4 in G is equal to. So what is the answer? So remember, it's a complete graph, 6 vertices. Complete graph, 6 vertices. Remember, it's undirected also. Complete graph with 6 vertices, undirected. A, B, C, D, E, and F. It's a complete graph. Complete graph means everywhere path is there. Everywhere path is there. Complete graph means everywhere path. Everywhere path is there. Everywhere path. When you say complete graph, everywhere path is there. Right, fine. Now observe. Now observe now. Everyone listen. Everyone listen. If vertices of G are labeled, then number of distinct cycles of length 4 in G equal to. If vertices of, right, see, if vertices of G are labeled, then the number of distinct cycle of length 4 in G is equal to. So let's see this one. Number of vertices, see this one. If the vertices of G are labeled, then the number of distinct cycles of length 4. Distinct cycle of length 4. Let's see. So length 4 you want. Out of 6 vertices, select 4 people first. Out of 6 vertices, first select, right, 4 people. So let us assume that I selected these people. I selected these 4 people. See, 4 people you select, 4 length cycles will come. 4 people, if you select 4 length cycles will come. Out of 6 people, select 4 people first, 6C4. Now, with those 6C4, these many ways you can select. How many cycles possible? Let's check here. Those are, listen, those are A, B, A, B, E, C. A, B, E, C. Everyone try to understand. How many cycles possible? Remember everyone, with these 4 people, because of complete graph is there. Complete graph means every possibility there. With the 4 people, the number of cycles possible is 4 minus 1 factorial by 2. We are already done so many places. So many places this formula there. Number of Hamiltonian cycles. Number of Hamiltonian cycles with n vertices, which is nothing but same only here. Number of Hamiltonian, right, cycles with n vertices, same formula, n minus 1 factorial by 2. If anyone having any objection, let me see this one. A, B, E, C, house are. See this one? If you want, you can check. A to B you go, B to E you can go, E to C you can go, afterwards A. Right, that is a one. Next one, see this one, A, B, and E, right? So A, B, right? E in the place of E, just swap it. C, A, C, right? E followed by A. Next one, I think I swapped E and right, I swapped E and C. Now I may swap B, A. Let me write now. B place I will write B place I will write C. Right here, B, E followed by A. Next one, A, C, right? So here, A, C, here. So E, B followed by A. Next one. I think C also over. Similar way do E also. A, B, sorry, E, B. I think C. C, B, and A. Next one, A, E, right? B, C. So yeah. So like that, 3 factorial. 4 minus 1 means 3 factorial, 6 people. These all are 6 people. These all are 6 people. Now understand. Now understand one more thing. Now understand one more thing. Everyone understand. Everyone understand. See this one? A, B, C, D. Carefully understand everyone. A, B, C, E. Understand this. See this. I'm using another color also. See, whether you go like this, one cycle, whether you came like this, one cycle, both are same. If you come in the reverse order, if you come in the same order, that entire thing is one cycle. See, you went like this, same cycle, you went like this, same cycle. So what I want to say, reverse also same. So to this one, if you see reverse, if you see A C E B C, A C E, right? See this one, A C E B A, A C E B A. These two are same. These two are same. Reverse. Next one, A B C E A. So reverse, if you see A E C, A E C B A. This one. These two are same. Right? In the similar way. In the similar way. These two are same. That is the reason half. Half is came like this, 6 by 2. 6 by 2, so 3k. 6 by 2, 3k. Try to understand. And one more thing, understand. Everyone listen. One more small story I want to say. A, B, C, D. This is also one more small story. A, B, C, D. Can everyone understand this? A, B, C, D. It is also very interesting point. A, B, C, D. See this one. If you come from A, one cycle. See this one. If you come from A, one cycle. If you come from C also, same cycle. If you come from D also, same cycle. So what I mean to say is, right, starting from A, how many there? Because of cycle, right? You can start from anywhere. You can start from anywhere. Starting from A, one cycle, same cycle you cannot say. Starting from C also one more cycle. Starting from D also one more cycle. You cannot say that because same thing only. Wherever you want, you can start. So this is also one cycle. So this is also same. Both are same. That is the reason starting with A enough. Starting with B also you no need to do. Starting with C also you no need to do. So finally problem is over. Now listen. Now listen. In the complete graph with 6 vertices, how many 4 length cycles possible? See the problem once again. A complete graph with 6 vertices, right? And then number of distinct cycles of length 4. Number of distinct cycle of length 4 possible. This is the answer for this. Out of 6 people, select 4 people. So 4 people you selected. With the 4 people, how many cycle possible? 4 element. Number of cycles possible. Which is equal to 6c4 into 4 minus 1 factorial by 2, which is equal to 6c4 means 6 into 5 by 1 into 2 into 3 factorial means 3 into 2 by 2. 2 2 cancel. 2 3's cancel. 3 5's 15. 15 3's 45. Answer is 45. Answer is 45. Answer is 45. Answer is 45. 64 into, right, number of cycles possible with the 4 people. 4 people cycles possible, 4 minus 1 factorial by 2. So 3 factorial by 2 means 3. 3. Right? 6c4 into 3. So find out. Distinct keyword is not there. Distinct keyword is not there. I think the same meaning is same. You may not count the same thing again and again. Right? To eliminate the ambiguity, he kept. To eliminate the ambiguity, he kept. Otherwise, how can you read the same cycle in different orders? Number of cycle will be same, na? Same cycle you cannot count so many times. To eliminate ambiguity, maybe kept like this. So this is a very interesting one. It is a very, very useful. Please take care. It is a very, very useful. Please take care. First select 4 people. 6C4. First select 4 people. Any 4 you can take. Because of it is a complete graph. Because of it is a complete graph. To go from anywhere to anywhere, path is available. Yes, yes, yes. Right? So if path is given, see this one. Everywhere path is there. Everywhere path is there. Select any 4. 6C4. Those 4, how many cycles possible? So we done this one many times. Number of Hamiltonian cycles possible. Number of Hamiltonian cycles possible. Many times we done. 4 minus 1 factorial by 2. Yes, yes, Shikhar. Shikhar, yes. Yes, Bhaiya. Shikhar Bhaiya, yes. Yes, you can apply. Same question he will ask you. Same question he will ask you. How many 3 length cycles possible? 6C3 into 6C3 into 6C3 into. So you selected only 3 people. 3 people, how many cycles possible? 3 minus 1, 2 factorial by 2. So which is going to be 6C3 only. Similar kind of thing you can expect. Similar kind of thing you can expect. Please, can you see this? Can you take care about this problem properly? Please take care this problem properly. Right. Let's move to next problem. It's a very, very interesting problem. It's a very, very interesting problem. Please take care. Now come to next. Yeah. He's asking in all these 4 graphs who are isomorphic. In all these 4 graphs who are isomorphic. Can you verify? Hello, sir. Now I am preparing for college as well as placements. Now I am preparing for college as well as placements. Okay. Okay, Prasad. Everyone try this problem. In all these 4 graphs, who are isomorphic? In all these 4 graphs, who are isomorphic? College. Prasad, if you cannot concentrate all, please concentrate college. If you cannot concentrate all, concentrate college and placements. If you can concentrate all, then concentrate gate also. Because college is more important than gate. Without affecting college, please try. Without affecting college, please try. Try everyone. Which are isomorphic here? Which are isomorphic here? Excellent. 9.29. I think Prasad, you can manage. Prasad, you can manage gate also because you are 9.29. You can manage. You can manage both. Manage both properly. Manage both properly. You can manage. You can manage both. Yeah, you can personally ping me also. This is our WhatsApp number, so you can personally ping me also. Still, if you have doubt, you can ping me. Still, if you have doubt, you can ping me. Yeah, isomorphic means every manner same. Isomorphic means every manner same, every way same, everywhere same, everywhere same. So let's see one important thing. Let's see one important thing. Let's see one important thing. Everyone understand? Everyone understand here? Everyone understand here? One small thing I want to ask you. So here, 1, 2, 3, 4, 5. Here degree is 5. One person degree 5. 1, 2, 3, 4, 5. Here no one is there with degree 5. Here no one is there with degree 5. So G1, G3 no relation. G1 having one person degree 5. G3 don't have one person with degree 5. So G1, G3 you can cancel. Next one, what about G2, G4, sir? In the G2 also, one person having degree 5. In the G4, no one having degree 5. No one having. So D option also you can cancel. D option also you can cancel. So the possibilities are either A option or B option. Either A option, B option. A option saying G1, G2 same. B option saying G3, G are same. Now I want answer from you. I want answer from you. What is the meaning of isomorphic? Everything same. So let's check one by one. In the G1, how many vertices? 6 vertices. G2 also 6 vertices. In the G3, how many vertices? 6 vertices. G4 also 6 vertices. That is okay. Can you say in the G1, how many edges are there? Count. Vertices should be same, edges should be same, degrees should be same, everything same. So vertices are same in the G1, G2. Next one, edges also count. Edges also count. Outside, if you observe, 6 are there. Right? Inside, if you observe 3 there, 6 plus 3, 9. But if you observe the G2, outside 3 edges are there. Outside how many there? I think 1, 2, 3, 4, 5, 6. I think outside 6 there, inside 3, totally 9. Edges also same. In the G1, G2, vertices same, edges also same, and one more. In the G1, one person having degree 5. In the G2, one person having degree 5. In the G1, right? Two people are there with degree 2. In the G2 also, two people are there with degree 2. So what I mean to say, this 2 is nothing but F, because F is having degree 5, 2 also having degree 5. Next one. In the G1, two people are with degree 2. So those are AE. It may be A, it may be E. Next one, in the G1, three people with degree 3. So these are D, E, F maybe. I think it looks like exactly same. It looks like exactly same. Now come to G3. Come to G3. Listen, everything should be same. Come to the G3. In the G3, if you observe, G3 there is a 3-length cycle possible. G3 there is a 3-length cycle possible. In the G4, 3-length cycles not possible. In the G3, 3-length cycles possible. In the G4, 3-length cycles not possible. If you want, you can verify. Isomorphic means every manner should be same. And one more, checking two graphs are isomorphic or not is an undecidable problem. You have to do manual checking only. If you think it is difficult to you, to everyone it is difficult. That is the reason they will give small graphs. They will give small graph. If anyone asks you, G1, G2 is isomorphic, G3, G4 is not isomorphic. If anyone asks you, what is the reason? In the G3, G4, G3 having 3-length cycle, G4 don't have. But in the G1, I think all looks similar. In the G1, all looks similar. Right? Perfect. I'm thinking everyone is fine. I'm thinking everyone is fine. Answer is A. See, two people are isomorphic to each other. See this one. A and B are isomorphic. A and B are isomorphic. That means A and B are isomorphic. That means A and B are isomorphic. That means, right? A and B, vertices same, vertices same, edges same, edges same. Next one, degree sequence also same, degree sequence also same, number of cycles also same. So I want to say one important thing, all same. Easiest way is all same. Simplest way of saying, how can I verify two graphs are isomorphic? All same, everything same, everything same. Vertices same, edges same, degree sequence same, number of cycles same, everything same, everything same, everything same. There is no other way to discriminate. Everything same. If you find out one thing also which is not same, then they are not isomorphic. If you find out one thing also which is not same, then they are not isomorphic. If you want, you can check G1, G2 are isomorphic. G3, G4 is not isomorphic. Yeah, whatever order you will take. So take both same order. Take both same order. If you take topological order, take topological order. Do both sides same. One side topological order, one side some other order, it is not. Take everything same. You want to do topological order, take that only, no problem. Everything same, everything same. That's it. Simplest of saying is everything same. There is no algorithm to verify two graphs are isomorphic or not. It's an undecidable problem, manual checking only possible. Right? I think today we done the, 9 problems we done today. Today we done the 9 problems. So tomorrow we'll see. I think let's go for a 10th problem also. Let's go for a 10th problem also. Let's go for a 10th problem. Can you finish it off? Yeah, let's do this also. Let's do this also. The 2 power n vertices of a graph G correspond to all subsets of a size n, where n greater than or equal to 6. Two vertices of G are adjacent if and only if corresponding sets intersect in exactly 2 elements. The number of degree 0 in G is. Yeah, whenever these kind of problems are given, so minimum thing you can do is take one example and check. Take one example and check. When formula based questions are given, right, take one example and check. If really required, we will go for proof and all. Take one example and try. 6 vertices are there. Sorry, 2 power n vertices of graph G correspond to all subsets of sets of size n is equal to 6. Okay, fine. Now let me try once. N is equal to 3. He said n is equal to 6, so it may become bigger. I am taking n is equal to 3. If really required, we'll see. N is equal to 3. Those are 1, 2, 3. Those are 1, 2, 3. Next one. What is saying? The 2 power n vertices of graph G corresponding to the 2 power n vertices of graph G. Find out the subsets. 2 power n subsets are there, right? 2 power n subsets. Find out all. 5, only 1, only 2, only 3, only 1, 2, only 1, 3, only 2, 3, only 1, 2, 3. Okay, those are okay, fine. These all are the vertices of the graph. Listen, these all are vertices of the graph. These all are vertices of the graph. These all are vertices of the graph. Okay, fine. Now some people are asking, sir, if these all are vertices of the graph, What about edge, sir? Sir, what about edge? Can you see the graph and talk? Two people are adjacent. See this one. Two vertices of G are adjacent if and only if the corresponding sets intersect in exactly two elements. Two vertices of G are adjacent if and only if the corresponding sets intersect in exactly two elements. See, exactly two elements intersection should be done. Means intersection is two people should be there. So you only say if you do intersection these two people, if you do intersection of these two people, intersection will come 1 3. Yeah, they are adjacent. If you do intersection of these two people, if you do intersection of these two people, I think intersection is 1 2. Yes, right. But one small question I want to ask you: one person, if you do intersection, one person, if you do intersection with anyone, you don't get the intersection as two people. So remember, two people, right? Two people are adjacent. After doing intersection, if two elements are common, you do anyone with this person, definitely intersection cannot be two people because he have only one person. So he is not adjacent to anyone. He is also not adjacent to anyone. He is also not adjacent to anyone. He is also not adjacent to anyone. The people who are not adjacent to anyone means degree zero people 4 are there. But remember, n value 3. Degree zero people are 4. Degree zero people are 4 people there. So 4, which is nothing but n plus 1. So what he is asking, you can see once. Two vertices of G are adjacent if and only if the corresponding sets intersect in exactly two elements. The number of vertices of degree 0 in G is, the number of vertices degree 0 in G is, I think 4 people, n plus 1. Is it okay? N is equal to 3. Subsets are 2 power n. These all are subsets. Graph vertices are these subsets only. Two people are adjacent. Their intersecting contain two people. 1 2 and 1 2 3 if you do intersection 1 2. 1 3 1 2 3 if you do intersection 1 3. So like that you have to do. So right, but he's asking intersection should be two people common. He's having only one person. How two people can common? He's having only one person. How two people common? So definitely their degree will be 0 only. Definitely their degree will be 0 only. Some people are saying, sir, this is 2 3. Can't you say this is the degree 0 possible? No, because this one if you do two people are there. This one if you do end operation with 1 2 3, you will get 2 3. So there is a one edge. But these people never get any edge because they themselves having one vertex, one point. Intersection, you do one point with anyone, you cannot get two. So answer for this one is C plus 1. Just so answer this one is going to be option C, n plus 1. Do manual checking. It is a very simple problem. It is a very simple problem because he is asking number of vertices with degree 0. Number of vertices with degree 0. That is the reason this problem became easy. It looks so scary, but actually it is very easy. It looks so scary, but our problem is actually so easy. The only thing is you have to do little bit of work. Is it okay? N is equal to 3, subsets are 8. Two people are right. Subsets are 8, which are vertices of the graph. Two vertices are adjacent if their intersecting point contain minimum 2. So you got to know answer is 4. 4 people having degree 0 because they have one vertex. If you do intersection, how you get 2 points? It's not possible. Most of the problem by substitution you will get. Most of the problem by substitution. Whenever formula based question came, please try to substitute. Worst case you can go for proof also. Worst case you can go for proof also. Yeah. Can we move to next? Can we stop it? So remember everyone. Remember everyone. 300 problems we are going to cover. 300 problems we are going to cover for the discrete mathematics. Right? So you please post. Everyone, please post whatever difficult problem you will find out. Whatever difficult problem you find out, please post in our groups. Please post in our group. If you are not there in the group, please ping us. If you are not there in the group, please ping us. We are going to help you. We are going to help you. Thank you so much. See you in tomorrow's class at 7 p.m. See you in tomorrow's class, right, at 7 p.m. Right, perfect. Thank you so much. Yeah, good night. Good night, everyone. Tomorrow, I will try to cover 20 problems. Now, 10 problems I done. Tomorrow, I will do, in my opinion, tomorrow, I will do minimum 20 problems. I will try. Thanks. Thanks, everyone. Good night.